certain county of Great Britain 30 years ago. Biologists observed that the population doubles every 6 years, and the new population is 100,000. So what was the initial size of the squirrel population? So your doubling is 6 years. It's over 30 years that we're looking at. I don't know what the initial population was, but I have how much? And now the population is 100,000. So my answer, my total that I have here is 100,000 squirrels that are ready to be hit. Okay, so there is our equation. I want to know what the initial population is. So that's all you have to do is plug in the stuff you have. The left side of the equal sign is always your total, whatever you have at the moment, basically. All right, so now we just solve this. We want to do 2 to the 30 over x. What is 30 over 6? And what is 2 to the 5th? 32. So I have 100,000 equals 32 times the initial population. What am I going to do now? Divide by 32. So what is 100,000 divided by 32 when you need to get any calculators? Everybody do it, or I'm giving you massive homework over the weekend. I'm tired of you not participating. I know you're wonderful and you work very hard.
31.5.
Everybody check, make sure she did it right. She did it right. The initial population of the squirrels in this area was 3,125. That's n of 0. That's important because now you look at part B. Estimate the squirrel population 10 years from now. So part B would be, I want to know what it is going to be if it started with 3,125 times 2. Instead of 30 years, what are we looking at from the time of the initial population? 10 years from now would be how many years from the initial population?
It would be
This was 30 years ago.
40.
40, thank you. And it doubles every 6 years. So now you have to figure this out. What's 40 divided by 6 on your calculator? That's going to be your exponent. 6.6 repeating. So you need to put this into your calculator and try to figure it out. Push equals and tell me what you get. Say it louder, please.
333,400.
So 10 years from now, there'd be 317,180 squirrels. Good. All right. Pretty simple. All right. And then you were also given, or you weren't given this, but we're going to go over it, and it was part of your assignment. It's called the exponential growth and titled relative growth rate. So that would be the title of your poster board if you're going to make a poster board. So we have n of t equals n of 0 times e to the r times t. Here we have 2 raised to t over a. Here we have e to the r times t. R is the relative growth rate. T is time. That's your initial amount. By now you should be understanding what those pieces are. For your final exam, you got to make sure you know these. It's either up on the wall or you have to have it memorized. Okay, so let's, which one? Number 7? You want to do number 7? Somebody didn't do that. Population of a country. Okay, a certain country, doesn't say what country it is. Population of a country has a relative growth rate of 3% per year. This is number 7. 3% is 0.03. That's your R. The government is trying to reduce the growth rate to 2%. The population in 1995 was approximately 110 million. That's your initial amount. 1995 was, what did I say? 110 million. Oops. 110 million in 1995 times E. And the projected population for the year 2020. So if we started in 1995, how many years has passed when we get to 2020? 25. So that's your T. So we're beginning our evaluation in 1995 at 110 million. How would you do this now? What do you do? Yeah, just put it in your calculator and figure it out. E to this amount, 0.03 times 25 times 110 million. You should get an answer. Work it out. Tell me what the answer is. Yeah.
232,870,000, or to estimate 233 million.
Is it 33 or 23?
No, 33.
232,
232.
but that's like
243 times that.
Yep. Okay, so 232 million people. Over a 25-year period, it grew 122 million.
Bless you.
Okay? Part B says the relative growth rate is reduced to 2%. So the only thing difference in Part A and Part B is this. Part B, I'm just going to make this 0.02. Change it to a 2% and see what happens. That's all you have to do on number 7. 2 different problems, 2 different rates. Any questions on that? All right, let's move on. Here's the next one. Radioactive decay model. So this would be the title of your poster board. So M of T equals M of 0 times 2 to the negative T over H. Okay, M of 0 again is your initial amount. On these problems, we're probably going to call it mass. T again is your time. H is your half-life. So there's our model. You're also going to use a model that looks a lot like this. M of T equals M of 0 times e to the negative r times t. R is the natural log of 2 over h. So these 2 formulas, basically, we're going to do the same thing. E is a little bit more accurate, but you have to go into your decimals to really find out. All right, so the problem's going to tell you which one to use, but really, it's going to be about the same thing when you're done, depending on which one you use. Okay, so let's do number 18. Half-life of cesium-137 is 30 years. So that's your half-life number. H is 30 years. And suppose we have a 10 gram sample. So the function m of t equals m of 0, 2. We're going to use this top one here. So number 18. We have 10 gram sample. And this is the decay model. So this is what you're going to have when you're done. M of t equals what happens after it decays. So we're starting with 10 grams. All right? Times 2 to the negative t. The half-life was what? 30 years. So that was part A, coming up with the actual problem. Here's your initial number. Half-life is 30 years. Basically, all these equations are, formulas are, you're just plugging in what they give you. It's not always that easy, which we'll see here in a little bit. I'll do a problem where you gotta use your brain a little bit. But I want you to think about your half-life. In 30 years, we're gonna have 5 grams. In 60 years, what are we gonna have? 2.5. In 90 years, what are we gonna have? 1.57. Half of 2.5? 1.25. So in 90 years, in 3 cycles, we'll have 1.25 grams. Alright, so let's read what it's asking. My point is, use a little common sense with what we're doing so that when you get an answer, you know if you're way off base. That's all. B, find a function. We're going to use this next function, which is a decay model. M of t equals m of 0 times e to the negative r times t. That models the mass remaining after t years. Okay? So minus t over 30. So here, this is saying use this formula, but set it up the same way. No big deal at the moment, everything's still the same. I'm sorry. Negative r times t. But r is the natural log of 2 over h. What was h?
Um,
30. That's your half-life. H is your half-life. Okay? H is half-life. So r is the natural log of 2 over 30. So everybody figure out on your calculator the natural log of 2. Don't forget, on your calculator it's going to do that. Make sure you do that before you hit the division key. Natural log of 2 over 30. What is it?
0.0231.
Is that correct?
Yes,
Alright, now it's negative r, so make sure you change the sign of whatever it is you get. Times t. Alright, that's part B. If you're going to use this formula here, you got to make sure you remember this. That's how you find the r. Okay, how much of the sample will remain after 80 years? So what's 80 stand for?
Time.
Well, time, which is what in the formula? T. It's over 80 years. Your half-life is 30 years. We just want to know what the population, or what the mass is going to be after 80 years. So T is 80 in this case. So on your calculators, you got to do this right now. Again, it's just filling in the information, but obviously if you don't understand what a half-life is versus the time, then we're in trouble. Okay? Everybody calculate this, please. Now remember, we said at 90 years it's going to be 1.25. We're not quite to 90 years, it's to 80 years, so we're going to have more than 1.25. What? So if you have something other than 1 point something, you're way off. What do you have?
1.57.
Yeah, so 1.57 grams. Not quite to 1.25 yet. It hasn't decayed that far yet. Anyway, get that? Who got 1.57? Okay, good. Alright, so that's a radioactive decay model. So this is a good example of what your poster board should look like. It's funny, I don't have any poster boards yet. Everybody must love their grade.
It's not working. It's times 80. It's times 80. Times t is our negative r times
Okay. Alright, that's using the radioactive decay model. Let's do Newton's law of cooling. Actually, you want to do one more of those?
Yes.
Okay, we'll do one more of those. Thank you.
God bless you. God bless you.
Alright, we're going to do number 24.
Hold on, I might get rid of
Number 24. Carbon-14 dating. Some of you might go into archaeology, you may go into the field where you need to understand how old something is, who knows. This is kind of what we use to do this. The burial cloth of an Egyptian mummy is estimated to contain 59% of carbon-14 of what it contained originally. So how long ago was the mummy buried? And the half-life is 5,730 years. Okay, so we want the decay model. M of t equals m of 0 e to the negative r times t. I don't know what the original amount of carbon-14 was. I do know I have 59% of it left. So this is the current amount, the total amount of what I have. I don't know the original amount when it started before it started to decay. So we're working this problem backwards. I do know that I had 59% of the original or the initial amount. I don't know the initial amount. R is the natural log of 2 over the half-life. What did it say the half-life was?
5,730.
What?
5,730.
5,730. Calculate that for me, please.
1000121.
Did I already give you these?
No.
Times 10 to the negative 4. With your decimal 4 places left. If you have it times e to the negative 4, that means that e is not this e. It's a capital E, which means 10 to the negative 4. Move your decimal 4 places to the left. So when you do your homework tonight, make sure you're looking on your calculator and don't say it's 1 point something when it has e to the negative something. You got to move the decimal that many places. So what is it again?
0.000120.
Okay. Times t. And it's a negative r, so that needs to be negative. Or if it was negative on a calculator, you make it positive up here. Again, this problem is great because you have to work this backwards. Now you can't solve an equation if you have two variables or more variables. And we have m of 0, that's a variable, and we have t. So I can't solve this unless something cancels out. How would I start to solve this equation? Can I divide by m of 0? Isn't the goal to get your exponential by itself? Isn't that what you're supposed to do when you're solving exponentials?
Yeah.
Good. So I need to divide off the m of 0. And notice that the m of 0's go away. Now, what did you learn to do 2 days ago when you have an exponential by itself? Take the log of both sides. In this case, we're going to do the natural log of both sides because we have e. Okay, so what is this answer over here?
Negative 0.000121.
It's just the exponent. Good job. Times t. Equal to, and then you got to tell me what the natural log of 0.59 is.
Negative 0.276.
Now it's algebra. How do I solve that problem? How do I get t by itself? Divide. So divide this negative number by that negative number, you'll get a positive number. $4,360. What does that number represent?
T. Just
What units? Seconds? Years? Hours?
Say pounds.
You got a mummy.
Oh, 40.
Years.
Years. Okay? So the stupid thing's been in there for 4,360 years. I'd really like to know how they figured out that the half-life is 5,730 years. But whatever. Yeah, that's another day, I guess. So, the whole point of this problem, there's a couple things, but really the main point is that you had to work this backwards. You were given the answer, and you had to tell me how much carbon-14 there was to start with. All right, last thing. Newton's law of cooling, and then Monday we'll do another set of formulas. So all you people that like dead people, Newton's law of cooling. Now, if you want to go into forensics, or you have to go into that type of field where you have to identify how long something's been dead, or you can just use it for other things too. How long it takes something to cool. But the cool part about this is being able to go to a crime scene and calculate the time of death. So this is what they would use. We're going to do number 26, but here's the formula you can put on a poster board. Capital T of T is really talking about temperature. Capital T is. This is capital T sub S. This is the surrounding temperature of the object.
Is it something they actually use? Like,
I don't know, never done it before. No, I mean, I assume they use this. Somebody's getting 6 figures.
or
I don't know how much they get paid. Some of those guys don't get paid anything. Huh? What'd you say?
It's just, I thought they got paid a lot.
Some people do. It all depends on what position it is. Sometimes it falls to the coroner, which doesn't get paid very much. If you're gonna do an autopsy, those doctors might get paid a little bit more. The object, okay, the temperature around that object at the time that you're doing the calculation. Okay, so if it's 60 degrees outside, 60 degrees would be the outside temperature, or the surrounding temperature, okay? D of 0, that's the initial temperature difference. What the temperature would have been before it all began, and then what the temperature is now. Okay, we'll do a problem you'll understand. And then D of 0, it's times e to the negative k times t. T is time, but k is what we call the positive constant. Alright, so that's a nice neat poster for you. Let's do a problem. Let's do number 26. Okay. Now the time of death is what we're looking at here. Newton's law of cooling is used in homicide investigations to determine the time of death. The normal body temperature is 98.6 degrees Fahrenheit. It's the normal temperature. Immediately following death, the body begins to cool. It has been determined experimentally that the constant in Newton's law of cooling is approximately 0.1947. That's K, so put a negative on it. Assuming that that time is measured in hours, that's what we're looking for here, hours. Suppose that the temperature of the surroundings is 60 degrees. So the surrounding temperature is 60. So that's your T of S, that's your temperature, 60 degrees, surrounding object. Find a function that models the temperature T hours after death. Okay. if your temperature initially was 98.6 and the surrounding temperature is 60, what's your initial temperature difference? 38.6. That's the V of 0. E raised to the constant, positive constant, times time. So that is part A. Very simple, surrounding temperature, and then the difference of what your temperature would have been before the death, obviously, 98.6 minus the 60. So you can set up the problem. Really what you're doing at the time, if you're doing bodies, is this number is going to be the same. These two numbers are what's going to depend on what's happening outside, whatever the temperature is. Obviously, this would change if that was different. You just figure those things out. So part B. If the temperature of the body is now 72 degrees, so the temperature now is 72 degrees. How long ago, or how long has the body been dead? So that's, you're finding t, and here you're going to have to use your logarithms to figure this out. How do I get t by itself? What do we want to start doing? Start hacking away at it. Subtract 60. So 12 equals 38.6 times e to negative 0.1947 t. We subtracted 60 from both sides. Now what should we do? You got to get the exponential all alone. Divide by 38.6. So take 12 divided by 38.6.
Is that 72 minus 16?
60.
Oh.
I don't know why I put 60
It's
up there.
0.31. Okay, we want to.
Point. That's right. We what?
0.3108.
I just happened to read this.
What's funny is I actually wrote down what
Right.
72 minus 60 was, not 72 minus 16. That's the weird part.
You all right today?
No. No, actually not.
Oh,
Alright, now is the exponential by itself? What do I do?
Natural law.
Natural log of both sides. So you're going to have to take the natural log of 0.3108 and the natural log of that. What's the natural log of?
Negative 1.168.
Agree.
Is that right?
Yeah.
Now what do I do?
Divide.
How do I get t by itself?
6.
Bailey. Negative 0.1947. And a negative over negative is going to give you a positive. Body's been dead for 6 hours, approximately. Okay? And I know why it's important to make sure you have these formulas. Not only you got to be able to put problems or substitute the values, you got to really have a common sense of what the answer is about to be. And also, like the problem we had over here, make sure you know, there's lots of things you don't know. You're hoping that things